Now we're going to look at how we can use hydrostatic pressure to calculate out pressure differences. And we have a device called a manometer. And the simplest form of the manometer is the barometer. So a barometer is used for one thing and one thing only, and that's measuring atmospheric pressure. The way that you create one is you take a dish of mercury, and then you take a tube filled with mercury and you insert the open end into the basin of mercury. Why are we using mercury instead of water? As we talked about in a previous lecture, mercury is much more dense than water, so you need a much smaller height to measure out those differences. Now, what we're going to do, and the way that we're going to analyze all these manometers, is we're going to exploit the idea that a fluid at the same depth has the exact same pressure. So after we identify where the fluid has the same depth, we're basically going to do kind of a pressure balance around that point. We're going to calculate the pressure all on one side, calculate the pressure all at the other side, and they should equate. So if we look at this picture here and we look at my barometer, you'll notice that this surface of the fluid here is completely in line with that dot. Now if we look on the left-hand side, this is open to atmosphere. So we'll call the open area 0.1. We'll call this dot here, call the open area 0.2. We'll call that dot over there 0.1. And so I know something about the pressure at 0.2. Pressure at 0.2 has to be atmospheric pressure, because the only thing pushing down on that is atmosphere. So just as an aside, atmospheric pressure is 14.7 psi at sea level. Where does that come from? Well, that's the hydrostatic pressure of air at sea level. So you go up to the troposphere, 20 miles or so up in the sky where the atmosphere begins, all the way down here. So you take that 20 miles, you multiply it by the specific weight of air, that's where you get 14.7 psi. That's why when you go to Denver, the air pressure there is somewhere on the order of 8.5 psi, because you're only going 19 miles down instead of 20 miles down. Okay, so now we look at the other side and we kind of look at what we've got pushing down at 0.1. Well, I do know that the pressure at 1 is equal to the pressure at 2 because they're at the same depth. But now I look, I've got this hydrostatic column of mercury pushing down on it, and then I have whatever vapor is pushing down on top of the mercury. Another reason that we use mercury is, well, if that's the gaseous stage up there, the vapor pressure of mercury at room temperature is 2.3 times 10 to the negative 5 psi. That is so small it's basically 0. So in the calculation we will figure that it is 0. So the pressure at 0.1 is going to be equal to that vapor pressure of mercury, because that's what's pushing down on top of the column, plus the hydrostatic force of the column of mercury, so the gamma of mercury times the height of that column. Now, we've said that the vapor pressure of mercury is basically 0, so that's going to knock out. So the pressure at 1 is basically gamma Hg times H. And we will rearrange this in terms of H, because that's what's really easy for us to measure. So H is going to be the pressure at 0.1 divided by the specific weight of mercury, which is also the pressure of atmosphere divided by the specific weight of mercury. And actually, this is how we calculate out atmospheric pressure. So a lot of times you'll hear in the news when they'll talk about the barometric pressure is so-and-so millimeters of mercury. Typically, I think it's around 30 inches of mercury or so. And the way that they usually report this is it's in head. It's in that head rating. It's that inches. You will not hear them say on the news that the atmospheric pressure is 14.7 psi. So actually, let's do that right now. Let's calculate out what the height of the column would be at atmosphere. So H is equal to 14.7 psi. We're going to want to convert that over to feet. And the reason that we're going to want to do that is we look up the specific weight of mercury. It's 847 pounds per square foot. So we take this 12 inches divided by 1 foot. We square that up so all the units work out. And so what we end up with is 2.5 feet of mercury which is about 30 inches of mercury. And so we have to remember when we're talking about head ratings, especially when we're measuring pressure with a barometer, we have to go, okay, it's this linear measurement, and then you have to tell it what fluid it is. Because 2.5 feet of mercury is much different than 2.5 feet of water pressure-wise.